Good morning.
Good morning.
Let's see, are there questions? First of all, I was just going to go through code examples. I don't think I need the notes open, but let me open them just in case. Are y'all playing with Racket?
Having a lot of fun.
It is fun. I think we're down to the end here, but I want to make sure. Whoops, this is not right. There we go. Okay, let's go through constructing some of these things. So we did factorial the other day. I'm going to start to produce these things up here so I don't have to keep rewriting them. So I'm going to define list one. Oh. Okay. If I run those, I have L1, L2, and L3. Okay. So let's do a simple sum function. In other words, we're going to just rebuild from scratch the plus operator. And I bring in a list, so I'm going to use L for list. Okay, so I've left the body of this thing empty. Let's walk through the thinking here, the rationale. We're going to do recursion. So that means that what we're going to do is gobble up this list and recursively call the function on the remainder of the list. So before I did this with factorial with a number, right, with just n, and I kept decrementing the number each time. But now I'm going to do it on a list, so you start to see how we work with the lists. If I said, give me the sum of an empty list, what would you do? What would you give in as an answer?
Zero.
Yeah, I think 0 is a good response. So basically, if I'm handed an empty list, the answer to this function or this function would return a 0. And what this does, this gives you a clue as to how to do the recursion. For myself, whenever I'm doing recursion, I always think, okay, what's the last thing that's going to happen? And then that helps me out. Now, if I give you a list that has one element, what do you return as the sum? One number, I should say.
You return that number, right? Since it's
Yeah,
the only one in the list.
Right, it's the only number, right? So you just return that number. And then if I have two numbers, it's clearly the first number plus the second number, right? But how would you do that recursively? You take the first number and you add it to whatever you get when you process the list that only contains the second number. And if we had three numbers, it's the same thing. The sum is going to be the first number added to the sum of the list that contains the second two numbers. So if I did if I did sum on the list of 1, 3, 6, 8, 9, then that's going to be 1 plus the sum of applied to that, right? But that's equal to 1 plus 3 plus the sum applied to 6, 8, and 9. See what's happening there? So basically what we're doing is saying that the sum of some list is equal to the car of the list plus the sum applied to the remaining elements in the list. Does that line make sense? It's putting down in bracket what we just said intuitively. How do I sum a list of numbers? I take the first element and add it to the sum of the rest of the numbers. And what's the last thing that's going to happen? I'm going to have an empty list and I'm going to return 0. So I need to check for empty list. If the list is empty, then do something. Otherwise, do something else. There's my if then else structure. Now we'll see if my parentheses are all stacked up appropriately in a minute. We said if we gave an empty list, what we should do, the expression that we return is 0. Otherwise, we take the car of the list and add it to the sum of the rest of the list. That looks good. I wonder if it's good. Oh, let's define empty. LE for empty. So if I apply the sum to L1, hopefully I get, ta-da, 15. Apply the sum to L3, 141. Literally, sum of L1 is sum acting on 1, 2, 3, 4, 5. Well, let's see. What's the first thing I do? Check to see if that list is empty. Is that list empty? No. Then it's going to be 1 plus whatever I get when I do the sum on 2, 3, 4, 5. And what's the sum of 2, 3, 4, 5? And we take 2 and add it to the sum of 3, 4, and 5. I'm not going to do them all. First of all, I'm going to lose track of my parentheses. Eventually, what we get down to is plus 1, plus 2, plus 3. Should have made a shorter list. The empty list. 1, 2, 3, 4, 5, 6. But what do we know the sum applied to the empty list is? We said that a good thing to say the sum of the empty list would be 0. So this whole thing becomes And finally, all the additions can happen. What you're doing, you're kind of stacking up all these dominoes. And finally, the dominoes can occur. 0 plus 5 is 5. 4 plus 5 is 9. 3 plus 9 is 12. 2 plus 12 is 14. 1 plus 14 is 15. This pattern you will see over and over again. Check to see if the list is null. If the list is null, then return some default value. If the list is not null, perform whatever operation you're interested in on the car of the list, and then recursively call the function on the cooter of the list. How would you do if I wanted to find the maximum element in a list? What would you do? How would you do it? I wonder if this looks. What's your thought process here recursively?
You could set the car of the list equal to the max, and then like pass the cooter of the rest of the list into like call it again, and then see if the car of that list is greater than the previous one.
Right. So it's going to be, let's see, what are we going to check for? If the list is of length null, it's a bad result. I'm going to go to the list as length 1. If the list is length null, what would you return as the max value for an empty list? I would say that's a bad answer, right? It's a perverse case. What if the list only had one element? What's the max element?
That one element.
That one element. Ah, okay. So that's going to be our check. I'm going to say if there's my check to see if it's a list of length 1. And if that's true, if the list is of length 1, I'm going to return that one element. But what if it's not true? Then I'm going to say, well, it's kind of like what Lynn said. She's still framing it a little bit of imperative form because she said set the max equal to, or something close to that. But instead of set the max equal to, then how about we just compare the car of the list with the rest of the list? So what we could say is the maximum element is either going to be the car of the list, or it's going to be the max element found in the cooter of the list. So we can say, so maybe I'll get this right. If whoops. I'm going to rewrite that. I'm sorry. So what are we doing in here? If, where you have another if statement. If the car of L is greater than the maximum in the cooter of L, there we go. Okay, now let's think about what that's saying. What does find max on the cooter of L return to you? Doesn't it return to you the largest element in the rest of the list in the cooter of L? And so all you're doing now is comparing and saying, well, wait a minute, either the first element is bigger than all the other elements or it isn't. So this find max cooter of L gives you the largest element in the remainder of the list. And then all you're doing is comparing car L against that. And so if that's true, we need something to do if it's true and something to do if it's false. If it's true, we return the car of L. If it's not true, then it must be the thing that was the largest element in the rest of the list is what got. I hope my logic's right. Okay, there's. So if it's a list of length 1, right, I always think about what the last thing you're going to do is. The last thing you're going to do is you're going to have a list of length 1. So if it's a list of length 1, it's clearly going to be that element. If it's not a list of length 1, then the largest element in the list is either the first element or whatever the largest is in the rest of the list. What's the largest in the rest of the list? It's find max on cooter L. I'm going to get an error, I'm sure. What do I have here? Too many of these things? Too few of these things? Wait a minute, why are you doing this? There, 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 there. Oh, I see. One too many. Okay, at least that's a procedure. Let's give it a list of one element. Well, that works. Now let's give it a L1. Oh, coincidentally the same. Ah, there we go. Oh. Helps if I can type. Okay. I can't believe that worked without any errors, quite frankly. Usually, you know how programming goes. There's usually an error. What's the largest in L3? It's 42. I'm going to move 42 into the middle of the pack so we're convinced that it's not just picking the last element. Okay, who's saying what the hell is going on here? Or is it unanimous? If you'll notice, this is a radically different way of thinking about the problem than the imperative. Yeah, and that's kind of a hard thing even until you get used to it. And then when you're doing more sophisticated things, even then it can be tough. And what happens to me is I start returning things and I think I've returned a car, but it's really still a list. And then the system gets mad at me because I told him I was going to give it an atom and instead I gave it a list. It's similar to the way we thought of the addition. You agree with that? The maximum is either going to be the first element or whatever the biggest element is in the rest of the list.
Is it, I think I might have kind of understood. Is it, if you don't find the first element, keep on searching through the rest of the list until you effectively find the next largest element? I think that's kind of
Kind
the
of, yeah, kind of,
way-
but you know, you're not, what you're doing in terms of, ultimately what you're doing in terms of the Boolean operator, the logical operator of greater than, is you're saying, you're doing a bunch of comparisons. You're doing basically greater than, I'm going to use the list of, I'm going to make up a list here. 3, 10, and 6. So what we're doing here is it's going to be the greater of 3 or the greater of find max applied to 10 and 6, which means it's the greater of 3 compared to the greater of 10 and find max operating on 6. Which means it's the greater of 3 compared to the greater of 10 or 6. So when you actually resolve that, the greater of 10 or 6 is going to be 10, and then the greater of 3 or 10 is going to be 10.
Okay, that makes more sense now.
But as Casey said, it's, you know, making sure that you're actually traversing the list correctly is, you know, it's kind of a tread carefully situation sometimes. And that's why, you know, doing these more simple ones is a fairly easy way to introduce you to it.
Right. Thank you.
The thinking is different, right? Because we've all done find max in the imperative world, and what did we do? We said, okay, we're going to assume the first one is the max, which is kind of what we're doing here. You assume the first one is the max and stick that in a memory location, right? And then every time we find one bigger, we replace it. But there's no memory here. There's just functions returning values. And so you have to reframe that as, I'm going to take the first element and compare that to what the function returned for the rest of the list. And then it's recursive from there on out. It's, you know, turtles all the way down. From there you say, well, what's the largest of the rest of the list? Well, it's either the first element or the largest of the rest of the list. Yes, yes. And this is a completely valid form of recursion. And so what happens is you're stacking up a whole bunch of, you know, I'm calling them dominoes, but you're stacking up a whole bunch of function calls. And if you do it wrong, where you get into an infinite loop, you stack so many up that eventually you run out of memory. But if you're stacking up a whole bunch of these things, then you're waiting for that last situation where you can actually say, oh, finally, I got a concrete value that I can return. Now I can start doing all the operations. But you're stacking them all up. Just like before with sum, we stacked up all the addition operations. Here we're stacking up all the comparison operations. There is a form of recursion called tail recursion, which we won't get into, that resolves this memory problem by performing the operation immediately and carrying the result forward instead of stacking up all the function calls. My second, you mean this this thing. Yeah, this part is doing the comparisons actually. If the list is of length 1, there's nothing to compare. It's just that element. But if the length of the list is larger than 1, then it's there's something to compare. Yeah. So if you look, remember, we have if, and then here there's the first expression, which is the Boolean test. The second expression, what happens if that test is true? The third expression, what happens if that test is false? It happens to be that the false expression, you know, it's a nested if. So again, I have my Boolean test. And then the thing that if it's true and the thing if it's false. By the way, how would you find the biggest list out of multiple lists? Is you have to, oh, the biggest, so the biggest sum? Yeah, if you had a list of lists, yeah, you would do it that way. Right. And your homework is similar to that, yeah. Your homework is similar because you're, I'm providing rectangles and you have to find the biggest, a list of rectangles, you have to find the biggest rectangle, the biggest area. So the biggest sum, what we can do here is, let's see, this is just, we could do this a couple ways. Here's how I would do it. Here's how I would do it. Since we already have sum, let me check and see if this works. We already have sum, okay, and we know how to perform sum on an individual list, right? Except I need to have a list that I defined already. There we go. So we already have that. So what if I did this? What if I make a list out of now what happened there? Remember what the map function does. The map function applies this argument to a list. So it applied sum to L1, and it applied sum to L2, and it applied sum to L3, and it gave me back a list, right? So what I can do to find the biggest of, if I wanted to find which list summed to the largest number, I can run find max. And instead of inputting just a list, let me do it this way. Let's define L sums. I need to define to be whatever you get when you do the map of sum on all these lists. And that's L sums. L sums. And then I can do define L sums. Oh, not define, find max. There you go. So the uglier way that looks is like this. Find max of the list that you get when you map sum to, that's not going to work. Except I didn't spell find right. This is easier to understand, right? Because it's just a list that I fed to find sum. But where did that list come from? It came from mapping the sum method to all the lists. So you could do that either in place. I recommend spelling your function names correctly. There we go. You can do it either in place or you can do it separately. So I made a separate little definition, right, to define to define L sums to be the summation of all those lists, which gave me another list. This is going to happen to you a lot. You're going to be dealing with lists and you're going to produce other lists, and then you're going to do something with that other list. Getting tired of typing this. Okay, did that answer the question? So notice, by the way, how flexible that was and how few lines of code you have to deal with, because we've already leveraged the two functions that we made. Your code can be remarkably sparse, particularly if you develop little helper functions along the way. How about just good old-fashioned search? How would you do a search? Define search as being lambda. It has to take in two things, a list and a key. And then it's going to return true if the key is in the list and false if the key is not in the list. So what's your thinking? How would you approach it? Let's see, if I gave you an empty list, what would you say? Is the key in the list?
No.
No.
No, right. If I gave you a list of one element, what would you say is the key? How would you answer that? Is the key in the list?
Depends.
Right.
It is.
Just compare against that one element, right? So here's what we're going to do. You need to check, exactly. So you just check. So here's what I'm going to do. I'm going to say, if the list is empty, then no. Now, if I give you a list that's not empty, what you're going to do is check, 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 check. And when you get to the end of the list, it's going to be no. And otherwise, you'll have a true in there somewhere, right? So let me see if we do this right. If I do that on the list, oh, okay, yeah. So if Boolean test, true thing, false thing, my Boolean test is going to be to see if the list is null, if the list is empty. If the thing is empty, I return false. But what if it's not empty? Now what do I return? Well, what would you do? You have a list of one element. You check, right? So if that element is the actual, it matches the key, then it's true. If not, false. What if it's multiple entities? What if there's 3 or 4 of them in there? Let's go with our list of 3, 10, and 6 again. And we want to find, and we're searching on 7, let's say. Well, let's see. Is L empty? No. So we can say, okay, if the first element return true. If it's otherwise, I'm going to do search on the rest of the list. For 7. So how does that look in general here, in the more general case? Let's see. I'm going to just check. Okay, look, I've got a list that's not empty. If the first element is matches the key, I'm done, right? So I've got a list that's not empty. So if the first element matches the key, I'm all done. Return true. If the first element does not match the key, can I definitively say false?
No, you still have to check the other
I
two.
still have to check the rest of the list, right? So I have to search the rest of the list. Okay, so I'm going to search the rest of the list. Now notice search takes in two things, right? A list and a key. So I have to apply search to a list and a key. All right, there's that. There's that if then else. I think I'm missing a parenthesis. There's that if then else. There's that lambda. There's everybody. Let's see if we got it right. What's something in L3? Looks like it's working, right? L3 has 10 and 16 is in there. It looks like it's working. Basically, this breaks down into if the list is empty, return false. If it's not empty, check the first element against the key, and if it matches, great, you're done, return true. If not, just keep running the same, recursively call the same function on the rest of the list. See, the same pattern keeps coming up over and over and over. Check the length of the list. If it's empty or if it's one, you have a concrete action to do. And this matches, all search, all repetitive behavior has the same characteristics. You have to have a starting condition and a stopping condition and progress towards the stopping condition. And with recursion, your stopping condition is what we normally call the base case, right? Remember recursive set theory, right? How do you define recursive sets? You have a base case. And basically that's what you're doing here. You're establishing your base case. And then if you have not yet reached your base case, then you have to do something, but you're making progress towards the base case. Notice all of these have cooter L in them, cooter L. What are you doing? I keep shrinking that list down every time I call the function until finally I'm down to my base case. An example that I give here is filter. We need to go through that probably. If I was smart, I would have saved all these and then I could bring up the file, right? Filter is the next step up from search. So what filter does is if you give me a list of numbers and I only want numbers above a certain threshold, you're going to return a list that has all the numbers above that threshold. Now, what are we returning? The tricky part is this, what am I returning? In the in the sum example, right, the sum of the list example, we were returning a number. In the search, in the max, we were returning a number. In the search, we were returning a Boolean value. What if you need to return an entire list? Well, same trick. What's your base case? Your base case is an empty list. If I asked you to, hey, here's a list, give me all the numbers that are bigger than 6 in there, and I gave you an empty list, what are you going to give me back? An empty list, because none of them are bigger than 6, right? There's no numbers in there bigger than 6. But if it's not an empty list, then what are you going to do? Well, you're going to check the first element. And if the first element is bigger than the threshold, you want to include it in the list that you're returning. And if the first element is not, you're just going to not include it in the list that you're returning. Well, what's the list that you're returning? The list that you're returning is if your first element is in the list, it's your first element, and then the filter function applied to the rest of the list. And if your first element is not bigger than the threshold, then it's just the rest of the list. I did this wrong. I should have done a cons there instead of an append. Oops. Where am I? There I am. Let me. What does it take as input? It takes a list and a threshold, which I'm going to call T. Okay, so we're going to do filter greater than. Okay, if the list is empty, what are you returning? You're going to return nothing, right? Because there's no entities in that list bigger than the threshold. So I'm going to return nothing. But what am I really returning? Remember, you have to keep track of your data types here. We're returning a list. So I'm returning a list, an empty list. Otherwise, I'm going to check to see if the first element in the list is bigger than the threshold. If it is, I want to keep it. And I'm building a list. So I'm going to keep appending to this list or adding this list. So I'm going to say if the first element in the list is greater than the threshold, if car L is greater than T, right, that's the first element is bigger than the list. If that's true, I have to do something. And if it's false, I have to do something else. If it's true, what I have to do is append or add that element to the list. And the proper way is cons. I don't know why I did append earlier, but it's going to be cons, the first element, to the rest of the list. Well, what's the rest of the list? It's what you get when you apply this thing to the rest of the list. And where am I? T. One too many. There we go. Otherwise, I just return the rest of the filter function applied to the rest of the list. And the rest of the list is always Kudrail. There you go. There you go. Why does your code on PowerPoint have an extra filter? Filter, filter. I have no idea. That must have been a typo because I actually, you can see I coded it in Racket and then I just cut and pasted it out. So I made sure it was running. Yeah. But what I should have done is save the file. I'm sure I was playing around with them because you'll see I have multiple versions of this. So assuming I didn't make any mistakes, which is always a bad assumption. Oh, what do you know? Filter greater than, let's take like list 3 and everything that's bigger than 20 and see if I get an error. Oh, 42 and 23. Does that work? Well, shoot, easier to do this. Oh, that's how I get them, Casey. I forget what window I'm in. Filter greater than L3, 177. I get the empty list. Filter greater than the empty list, 5. I get the empty list. I get L3 back. Now, one of the things I show in the files here is I did a filter. I call them 1, 2, and 3. It's lousy. Greater than, less than, and equal to. And I wrote them all. And if you notice, they're all three. They're exactly identical. The only difference is in this greater than, less than, or equal to operator. But since we're allowed to put operators or functions into functions as functions, I can make a universal one, a generic filter that takes in the list, the threshold, and then tell me what Boolean operator you want. And now instead of creating 3 different versions of filter, I just have one. But if I want to filter high, I put in the greater than operator. And if I want to filter low, I put in the less than operator. And this again goes to this notion of, since Racket is a higher order language, it will accept functions as input to other functions. You can create these template functions and then have them actually perform different behavior by feeding them a different function to perform. In this case, it's that simple operator, but the function could be arbitrarily complex. You have a programming assignment due Monday. Is that true? That sounds right.
Yes.
Okay, now, so here's the question. Does that need to move? Yeah, I would change it to cons, yeah. If we're, yeah, so that one is, yeah, I don't see any reason why we can't move it back a little bit. What are the dates here? Let's do November 2nd, which is Monday. Yeah, there's no reason why we can't move that back. I'll move that back. Making a note to do that. Okay, so as you can see, play with this stuff. And then we'll keep doing this next week, right? Keep looking at different programs and mini programs like this. Okay. We started with just returning single values. Now we're returning lists. Next, we can start to return lists of lists or summaries of lists, you know, where the input is lists of lists. Okay. Okay, I gotta let you go. And I will see you all on Monday. Have a great weekend.